list three key lessons that you have learned, or the concept or the idea that you have actually learned and that you would like to implement in future in your service, those who are teaching, or in your research work. So that is to be bulleted. And the third and the last is to share the implementation plan. So if you have got some concept or ideas how you will implement those things, again, very short in brief, uh, 2 or 3 points that you will be writing in the bulleted form. And at the end, this entire thing will be actually uploaded to the Atal FDP sites, and probably for all the FDP programs that are being conducted by under the Atal scheme, it will be compiled, and then the analysis will be carried out. This is a brief overview of what will be done. And without wasting much time, I would like to introduce today's speaker. Uh, is Professor Arun Kumar from IIT Delhi. We were having a very close and old association. I was fortunately, you can say, attached with him, and then during the QIP program, I got the admission under his supervision. So I had that sort of affiliation. Uh, but unfortunately, I could not complete the PhD from there. But I got Commonwealth, and I went in UK and did my PhD. Uh, Professor Arun Kumar, he is in the Center of Applied Research in Electronics, the CARE Center, and he joined in 1997 and became professor in 2008. He served as the head of the center for more than 7 years. He has his BTech, MTech, and PhD degree from IIT Kanpur, and he was a visiting researcher in University of California, Santa Barbara in USA before he joined IIT Delhi. His area of research includes digital signal processing, underwater and air acoustic applications, human and machine speech communication, and multi-sensor data fusion. Uh, Very important, you can just guess that he has got 10 US patents, all granted, and these are all US patents. So he has guided 16 PhD and published more than 160 papers in reputed journal and conferences. He has been active in research as well as in project, and he has 72 funded research projects to his credit from the industry and the government, which is having a worth of more than 40 crores. And many of his projects have been now in the industry because of the technology transfer to the industry and the government. So he is a real practical engineer, where he has implemented the theory practically, and then it has been transferred to the industry, which have been used since long in different applications. He is also active at national level and international level committees, and in the defense field as well. He is presently the executive committee of Government of India's ambitious national language translation mission, with a goal to develop automatic speech-to-speech translation technologies in all the scheduled languages. He is also the deputy editor-in-chief of the IIT Journal of Research, and also the co-founder of the company that develops signal processing and AI-based technologies and product for speech-based human and machine communication. So I welcome you, sir, to this session, and I am sure that the participants over here will have a lot to learn from you. And I think also that you are the most appropriate person to start this program, which is catering into the speech signal processing. And because you are from the core speech as well as the audio signal processing group. So it will be very helpful for the participant to have background in this area from such a renowned person. And I thank you for your time and the effort that you have put in and agreed to our request. I would also like to thank the Atal FDP scheme that they have sanctioned this faculty development program and funded this program. And I hope that we will have a very fruitful interaction in this session. Over to Professor Arun Kumar, sir.
Yeah, thank you, Professor Farooq, for your kind introduction. I hope I am audible.
Yes, sir.
Yes, sir, you are audible, sir.
Okay.
Yes, sir.
So let me share the presentation from the iPad, and I will keep the video. Kindly confirm that you can see the presentation.
Yes, sir, we can see.
Yes, sir. Yes, sir.
Okay. Right. So thank you again for inviting me to give this talk. Now, since the topic is to do with automation of speech-related technologies, so the way I have organized this presentation is as follows. So after a brief introduction, we will look at the speech signal, the different acoustic classes, the characteristics, the speech signal production model, time domain processing of speech, linear prediction in speech processing. And the other aspect is the hearing mechanism, because several of the hearing processes of the human ear are also used in technologies related to automation. And finally, I will conclude. So I understand the way the lecture is to be split is we will have about 50 minutes of presentation followed by some discussions and then again another 50 minutes of presentation. So that is how the lecture will be organized. Now, speech-enabled automation technologies. So the requirement is that we have natural language interactions with computers, handheld and wearable devices. And for this, the key technologies that are required to be perfected with are speech recognition, text-to-speech synthesis, and then for compression purposes, speech coding, and other applications include speaker recognition, and then analytics. So we want to analyze the several aspects from the speech signal, because the speech signal is not just about the message content, it contains other information also, like the gender of the speaker, the language, the emotion of the speaker, and all these things can be inferred from the speech signal, which constitutes the topic of speech analytics. Now, this is a good time for those of you who are getting into this field, particularly from the Indian perspective, because there is a major thrust from the government of India to develop speech-to-speech translation technologies and all the relevant tools in the scheduled languages of the country. So the mission has begun. It is almost 1 year old now, and a huge amount of money, about rupees 500 crores, has been allocated. And I am happy to be associated with the mission as a member of the execution committee. So a lot of effort is being done, not only from startups, but also from academic institutes in terms of projects which will enable these technologies, particularly for the Indian context. So now, as I said, it is important for us to understand the speech signal to be able to do some research work and come up with technologies. So the aim of this lecture is to introduce you to the characteristics of the speech signal and also the important analysis tools for the speech signal. So to begin with, we will discuss the speech signal, the various acoustic classes and their characteristics. So you may consider this to be more of a speech and hearing science oriented lecture, where we understand the characteristics of the signal and their basic analysis tools. And now to begin with, what is the speech signal? It is the variation of pressure from the atmospheric pressure as a function of time caused by traveling waves from the speaker's mouth apart from the nostrils, cheeks, and throat. This is because the speech energy, the acoustic energy, also radiates from the nostrils as well as from the vibration of the cheeks and the throat. So all this either goes to the person directly who is in front of the speaker and the person listens, or it is recorded by a microphone and it is converted into an electrical signal for further processing, which could be for the purposes of telephony. One can compress the signal and transmit it, or do local processing. Now, most of the speech signal energy is concentrated in the band of 50 hertz to 7,000 hertz. And the human hearing band ideally is from 20 hertz to 20 kilohertz, although practically it is more from 50 hertz to about 17 or 18 kilohertz. And the bandwidth decreases with age. Now, when it comes to technological applications, there are certain commonly used formats for the representation of the speech signal. The most common one being the telephone band speech, where a bandwidth of 300 hertz to 3400 hertz is used for telephony purposes. For digital telephony, the sampling rate is taken as 8 kilohertz and the bits per sample is 16. So that works out to 128 kilobits per second. Now, We have another band which is called the wideband speech, which is from 50 hertz to 7 kilohertz. Here the sampling rate is 16 kilohertz, and the source rate works out to, that is the uncompressed signal rate, works out to 256 kilobits per second, assuming that 16 bits per sample is used, which is most common. Now, wideband speech is used for several applications, particularly for video conferencing and more so for voice over internet protocols or VoIP communication. Wherever the communication is done using loudspeakers, that is, the listening is done over using loudspeakers, where you hear with both your ears, that is binaural hearing, the wideband speech bandwidth is preferred for those applications because telephone band speech otherwise has limitations in terms of crispness of speech and intelligibility, etc. The third important format is the wideband audio, which encompasses the entire band of human hearing from 20 hertz to 20 kilohertz. And the commonly used sampling rate is 44.1 kilohertz, which is used in CDs and DVDs, and also sometimes 48 kilohertz, typically for DAT, digital audio tapes. So this works out to a source rate of 705 or 768 kilobits per second. Now, the most common measure of the speech is in terms of the sound pressure level, which is very closely related to the sound intensity level also. And typically we give the sound pressure level in the decibel scale, that is relative to a reference level. And this reference level is taken to be just audible sound. So just audible sound then becomes 0 dB, and what it means is that a sound which will be heard by 50% of the people from a group of human beings, and it will be heard 50% of the time, that is qualitatively defined as just audible sound. So that is taken to be 0 dB. And there is a corresponding intensity level for that. And all other sound pressure levels or intensity levels are given relative to this reference. So in this plot on the right hand side, you can see that whispering sound has a sound pressure level of about 20 decibels, and variation in normal hearing, normal speaking is between 55 to about 80 decibels. And above it, you have loud sounds like heavy traffic, rock concert, and the jet engines of an aeroplane. So this reference in absolute physical terms is 10 to the power minus 16 watts per centimeter square. So this is one unit that is in the decibel scale that we hear of the sound pressure level or the sound intensity level. And we know that if we are exposed to loud sounds of 90 dB or above for a significant duration of time, then it has the potential to cause permanent damage to the human ear. Now, in this plot, you can see the time waveform of a speech sentence. So this is recorded by a microphone and converted into electrical signal. So the y-axis will be the voltage, and the x-axis, which runs across several panels over here, is the continuation of the speech sentence. So this waveform, as we can see, is having various characteristics. Firstly, we can see that it is not a periodic signal. It has a lot of variation in terms of the energy. So the utterance here, the sentence which is being uttered here is, should we chase? So the initial part, we have the utterance sh, the sh sound, which is called as a unvoiced sound. So we will understand this a little bit more. And we see essentially if we zoom this out, we will be able to see that it is mostly a random noise like waveform. Thereafter, when we move to vowel sounds like oo, it has more energy and it is more periodic in nature compared to the sh sound. So these are some of the characteristics. The important point to note from this figure of the time waveform of a speech sentence are that the speech signal is a non-stationary signal. In the sense that its statistical characteristics change over time. So we generally say that the speech signal is a quasi-stationary signal. So speech signal is a quasi-stationary signal, which means that we can assume that the speech signal is statistically stationary for 10 to 40 millisecond duration for the purposes of analysis and modeling. Then we already saw that the speech energy varies over time. Also, that the speech signal can be nearly periodic and at times, especially for vowel sounds, and at other times it could be almost random noise-like. The energy of the speech signal relatively is very low. So during 1 second, it basically produces about 2 into 10 to the power minus 5 joules of energy. And comparatively, if we want to light a 100-watt bulb for 1 second, then it consumes 100 joules of energy. So you can see the enormous difference in the energy level of the speech signal compared to light-related signals. So it is because of this variation in the temporal characteristic of the speech signal that it is important to understand this and to be able to build applications most efficiently. Now, some of the methods for speech signal analysis pertain to time domain analysis techniques. So we have the measures like zero crossing rate, autocorrelation function, the pitch period, the voiced versus unvoiced speech classification. Frequency domain analysis, like computation of the fundamental frequency, also called as the pitch frequency, and formant frequencies. So I will discuss these in detail as we go along. Then time frequency domain analysis. So most notably the spectrogram analysis and cepstrum or cepstrum domain analysis. So if there is a question, I'm not able to view it. Maybe we can take up questions at the end, unless there is an important question where you can stop me and ask your question. But mostly we will have the discussion at the end of the presentation. Okay, now what I would like to do is to give Introduction to Spectrogram Analysis. Is there a question there? I can see. And we have two spectrograms. One is called as the wideband spectrogram. So these are time frequency, and this is a time frequency analysis tool. And the commonly used settings for the spectrogram correspond to wideband and narrow band. So as the name implies, in wideband, the resolution along the frequency axis is poor, it is wideband, and the plot itself is essentially three-dimensional, you can say. The x-axis corresponds to the time in millisecond, the y-axis corresponds to the frequency in kilohertz, and short time Fourier transform is taken of the signal, where the frame size for the short time Fourier transform can be varied. So here we have the frame size of 3 milliseconds in wideband spectrogram, and for narrowband spectrogram, the frame duration is longer, which leads to fine frequency domain resolution and correspondingly poorer time domain resolution. So the spectrogram as a tool is useful in understanding how the spectral peaks of the signal are varying over time. So this is sort of a picture which tells us how the important frequencies of the signal, the speech signal, are varying over time. And we will understand this more detail when we take up specific acoustic units for study. So we can see that the wideband spectrogram has vertical lines over here, which corresponds to the narrow time resolution, whereas the narrowband spectrogram has the horizontal lines, as you can see if you look at it carefully, and that corresponds to the fine resolution in the frequency domain. So both these together are used to get an understanding of the speech signal. In fact, there are so-called spectrogram analysis experts who can look at the spectrogram and come to a very good understanding as to what signal, what sound is being spoken. Of course, it has to be also taken in conjunction with other information, but there are people who can analyze spectrogram by themselves and be able to tell with a reasonable degree of accuracy as to what kind of sounds have been spoken. So this was just an introduction to spectrogram. Later on, we will use this for speech signals of various kinds. Now, when we talk of speech, we have a written mode, which is basically the alphabetic spelling, and then the pronunciation. So the spelling is also referred to as orthography, and the pronunciation is basically studied under the topic of phonetics. Now, as we know that in most languages, the way we write is not the same as the way we speak. And here is an example where we see that certain words, the E sound is written in different ways, but they are all pronounced as E. So we have what are called phonetic languages, like most Indian languages are considered as phonetic languages, in which the orthographic form matches with the pronunciation. That is, the way we write it is the way we speak, unlike English. And this has implications in terms of the dictionary or the lexicon that one has to refer to between the written form and the pronounced form. Now, some of the important terms when it comes to the study of speech are given in this slide. So one of them is phonology. So this is the study of how sounds are organized and used in natural languages. Phonetics is the branch of phonology that deals with individual speech sounds, their production, and their written representation. Then phone is a unit of sound in phonetics. So this is not language dependent in the sense that these acoustic units can be used to describe most languages. Then we have phoneme, which is a set of unique sounds which are specific to a language. So different languages would have different phoneme sets, whereas a single phonetic alphabet is used to describe sounds coming from most languages. Then we have syllables, which contain vowel as an anchor sound, and it may or may not contain consonant before and or after the vowel. So we can have combination of sounds like a vowel consonant, consonant vowel, consonant, and so on. So these are grouped as syllables. So syllables are generally the most natural basic units of sound in terms of pronunciation. For example, if we take a word like signal, so we speak out sig together and null afterwards. So sig, there is a very brief pause and then null. So this is a disyllabic word in which the anchor sound in between are the vowels E and A. Okay. Now, an important alphabet which is used in the study of speech sounds is called as the International Phonetic Alphabet, which is periodically revised, typically once every decade. So the last revision happened in 2015, and it is given by the International Phonetic Association, which is the oldest organization established in 1886. So the IPA provides the academic community worldwide a notational standard for phonetic representation of languages. And this comprises of a consonant table and a vowel table at the base level, and there are more details. So these two tables we will study in a little bit more detail to get a better understanding of the acoustic units of speech. Now coming to the speech production process. So sounds are basically of two types. One is ingressive sound and the other is egressive sound. So ingressive sounds are created when we inhale air. Right? So click sounds, for example. And egressive sounds are those which are created when we exhale air, like most of the time when we are talking. These are egressive sounds. Some languages, some African languages, for example, are predominantly made with ingressive sounds, whereas most of the other languages are considered as egressive sounds. So here the process comprises of the following. The lungs are filled with air. There is the contraction of the rib cage, which forces air from the lungs into the trachea, as shown in this sketch. And then we have the larynx, which contains the vocal folds. So essentially, if you hold this protruding part of your throat, then that is where you have the vocal folds. And the vibration of the vocal folds is what causes voicing. So this is referred to as voicing. So the period of vibration of the vocal folds is called as the pitch period. Now, not all sounds are created by vibration of the vocal folds. So if you hold the protruding part over here and utter a sound like sh, then you will not feel that the vocal folds are vibrating. On the other hand, if you utter any vowel sounds like a or z, right? So the vocal folds are vibrating. So sounds where the vocal folds are vibrating are called voiced sounds, and sounds where the vocal fold is not vibrating are called unvoiced sounds. So all vowel sounds, for example, are voiced sounds, whereas consonant sounds are voiced or unvoiced. Now this air is forced through the vocal tract from the vocal folds, which may be vibrating for some sounds and may be just open with as a narrow constriction for other sounds, that is unvoiced sounds. Now this air is forced through the vocal tract, which consists of the pharynx, the oral cavity of the mouth, and the nasal cavity. And another important organ in the creation of different sounds is the tongue. So the principal purpose of the vocal tract is to create resonances in the airflow. And the combination of these resonances is what creates different sounds. So these resonances are known as formant frequencies. Formant frequencies. And they are denoted by F1, F2, F3, and so on. So typically F1 is the lowest formant frequency or the resonance frequency, F2 is the next higher one, and so on. Likewise, the inverse of the pitch period is known as the fundamental frequency, and it is denoted by the symbol F0. So as I mentioned, the basic categories of speech sounds include vowels, which are all voiced and produced by exciting a fixed vocal tract with quasi-periodic pulses of air, because the vocal folds open and close. And vowel sounds have relatively higher energy compared to consonant sounds. Consonants can be voiced or unvoiced, and they are produced by a relatively constricted vocal tract. And because of this constriction compared to vowel sounds, they have lesser energy. And now let us look at the vowel sounds from the International Phonetic Alphabet. So as I explained earlier, these are basic acoustic units called phones. Now the symbols are given over here, and I will give example words corresponding to these sounds in subsequent slides. But what we want to understand from this figure is the way this vowel table is organized. And the words here that you see, close, open, front, and back, correspond to the tongue position, or more specifically the tongue tip position. So if the tongue tip is in front and it has a high position, right, which means that the vocal tract is almost closed, then we utter the sound which is E over here. Right? And similarly, the one at the bottom corresponds to a front tongue position but open, which means that it is in a lower position. Similarly, we have central and back. So this is how the different vowel sounds are organized, and we will see examples in subsequent slide. So the articulation of vowel sounds are given by the tongue high or low position, right? The tongue tip essentially, and the tongue tip front or back. The lips, whether they are rounded or unrounded. So for example, if you produce a sound like oo, then the lips are rounded. And whether they are nasalized or unnasalized. So English does not have nasalized vowels, but other languages like German, for example, has nasalized vowel sounds. So vowel sounds are characterized by the front position of the tongue or central position or the back position. And here are some examples for the front position of the tongue. So front and high position like E or I, capital I corresponds to the I sound like in sit, invite. Or you have the A sound when the tongue is in the middle position corresponding to aid, locate, and so on. Then in the central position, when the tongue is neither in the front position that is close to the lips or the tongue tip is not too far back, so that's the central position. In that case, you have sounds like the sound, the oo sound, or the sound, right? So these are corresponding to the central position. And then you have when the tongue tip is moved further back into the vocal tract, then you have these sounds that are produced corresponding to the high position, the mid position, and the low position of the tongue tip. So this is how vowel sounds, the articulation of vowel sounds is organized in the International Phonetic Alphabet. And the position of the tongue essentially creates a combination of resonance frequencies in the vocal tract, that is F1, F2, and F3. And the combination of F1, F2, and F3 together create a particular vowel sound. So vowel sound here, let us look at the time waveform. Now this is the E sound as in the word bead. So relatively we have seen that vowels have high energy. They are relatively periodic and they are steady state utterances in the sense that you can articulate a vowel sound as long as you have the breath to utter the sound. So here is the example waveform, and we see that this approximately periodic signal has the associated pitch period. And then we have the manner of articulation, which is represented by the rows. So the important ones are plosive sounds, nasal sounds, and fricative sounds. So these three I will discuss in a little bit more detail. So place of articulation I already discussed. That is where you create the constriction in the vocal tract with the tongue, right? So these are the different places of articulation. Now the manner of articulation. So this is concerned with the airflow, that is the path that the airflow takes and the degree to which the flow of the air is impeded by the constriction of the vocal tract. So if you completely stop the airflow, as in what are called stop consonants, and then you suddenly release the airflow. So this is complete occlusion. Or you have constriction, that is, you narrow the flow of the air, narrow the constriction for the flow of the air. So these lead to fricative sounds. Or you close the oral tract and pass the air through the nostrils. So these lead to nasal sounds. So let's first look at stop consonants, or what are also called as plosive sounds. So these are created by completely closing the airstream, building up pressure behind the closure, and then a sudden release of sound. For example, b, d, g, p, t, k. So in all these sounds, you close the vocal tract at some point and then build up pressure behind and then suddenly release the air pressure. So these are called transient sounds in the sense that they are very short duration sounds corresponding to 1 to 5 milliseconds. So here are examples of waveforms corresponding to these stop consonants or plosive sounds. So stop consonants can be voiced or unvoiced. So in unvoiced case, the vocal fold is not vibrating like D sound. So you see that initially the pressure is being built up and then suddenly the pressure is released. So you have this noise-like waveform. So these two characteristics together give an idea from the waveform that this is likely to be a plosive sound. Thereafter, you have voiced stops or voiced plosive sounds where the vocal fold is also vibrating, like in T sound. T, if you utter and hold the vocal folds, you can see that feel that it is vibrating. So this is characterized by the presence of a periodic aspect to the signal and also a random noise-like aspect once there is this release burst. So here are examples of spectrograms of stop consonants, which is again characterized by this gap where you build up the pressure and then suddenly release the pressure. So you have this gap and then the release of this pressure. Then fricative sounds are created by a narrow constriction in the vocal tract, which creates turbulent airflow. So an important characteristic of fricative sounds is the random noise-like characteristic. Now, fricative sounds are also unvoiced or voiceless, or they can be voiced. So sounds like f, right, th, s, s, right, sh, sh. So these are unvoiced fricative sounds, and as you can expect that the waveform of these sounds are noise-like. You also have voiced fricative sounds. So corresponding to the unvoiced sound like f, you have the voiced sound like v sound. So the corresponding voiced fricatives, the vocal folds are also vibrating. Otherwise, the vocal tract remains the same. The shape of the vocal tract remains the same. So this is again an important class of consonant sounds in terms of the manner of articulation. So here are examples of unvoiced fricative sounds, waveforms, and their spectrum. So the point to note here in terms of characteristics are that these are very weak signals. There is no periodicity in unvoiced fricatives, and the Fourier spectral magnitude will have one characteristic, which is that the spectral energy increases with frequency. That is, the higher frequencies have more spectral energy. Here are waveforms, the waveforms and spectrograms of fricative sounds, s, s, right, and th. So because of the random noise like waveforms, you can see the spectrogram also has a very broad spread of the energy as shown by these dark patches, right? So the y-axis being the frequency axis and the x-axis being the time axis. So this is the characteristic of fricative consonants. Specifically unvoiced, and likewise we have voiced fricatives. So voiced fricatives have a random noise like part which is riding on a periodic pattern of the waveform. The periodicity comes from the vibration of the vocal folds. That is, periodically you open and close the vocal folds. So and the corresponding spectrum of the voice fricative is shown in the lower plot. So we see the waveform and the corresponding spectrogram over here, the wideband spectrogram, and what we can see is that the spectrogram has these vertical lines which shows that it is a voiced sound, as well as the dark patches over here which show the formant or the resonance frequencies which are at the higher values of frequency. Then we have other sounds which I will not go into detail over here because there are very few numbers of these sounds and in terms of the frequency of occurrence. Like we have affricate sounds, which is a combination of the plosive and fricative sound like j or ch. So these are examples of what are called affricate sounds. Then you have nasal sounds. So for nasal sounds, the vocal tract is closed and the sound, or rather the air stream is radiated through the nostrils. And in English, we have three nasal sounds, m, n, and the ang sound. And examples, words where these nasal sounds occur are shown in this table. So nasal sounds are also voiced sounds in the sense that when we articulate them, the vocal folds are vibrating. So here are examples of the spectrogram of nasal sounds which have low to medium energy. They are periodic and they are steady state utterance in the sense that you can utter a nasal sound as long as you have the breath. So the spectrogram here shows several nasal sounds like the n sound over here, the m sound over here, and they are essentially similar to vowel sounds like e over here, except that they have lower energy, and therefore you can see that the dark patches are somewhat less dark, or they are lighter compared to the vowel regions. So this is, in short, the description of nasal sounds. Then we have liquid sounds like l and r. So these are two liquid sounds. We are not going into details over here. And finally, we have glides, where again you move from one position to another, like y or w sound. Right? So these are two glide sounds. So in a nutshell, this is the description of the basic consonant sounds and the vowel sounds that occur in the International Phonetic Alphabet. And as I said, the International Phonetic Alphabet is used to describe almost all sounds which human beings articulate in their respective languages. And this alphabet is updated from time to time based on some new sounds being discovered which cannot be put into one of the existing categories. So I think this is the right place to stop. After this, we will discuss about how speech sounds are produced, again because it is that knowledge is useful in making models which are then used for application. So with this background then, now we will be able to appreciate the speech signal production model and analysis of speech signals, which will follow. So let me stop here and we can have a discussion at this stage.
Thank you, sir, for the first session. I may request the participants, if they are having any query, please, they can put it on the chat box, and Professor Arun Kumar will respond to that. Or you can ask also, but we should resolve the conflict, because there are many participants and we should not have a crosstalk.
There's a first question here, sir.
Okay, so if the question is how
Speech signal processing is helpful in defense.
Okay. There are various applications in defense. I mean, firstly, if you are talking of defense equipment or let's say vehicles, you talk of tanks and aircrafts, there is a need to silence other sounds so that the communication coming from far end becomes audible. So that is the topic of speech enhancement. Then some of the interaction with the machine can be in terms of voice rather than through physical interaction through the hands. So that is enabled with speech recognition. Some of the information can be spoken out, not very important information can be spoken out, and that happens in aircrafts. So that requires text-to-speech synthesis, right? So these are some of the applications. They are being used to various levels. And then you have applications related to surveillance, that is in order to find out, or rather spotting of keywords, keyword spotting. In running telephone conversations, if certain words are being spoken, then an operator can be alerted. So that is the problem of keyword spotting. So there are several applications in the defense field. Okay, the next question is IPA chart updated from time to time? Yes, the IPA chart is updated from time to time. Before 2015, I think it was 2005. So as I said, once in a decade on the average, the IPA chart is updated with new research and new sounds which cannot be put into the existing category of sounds. So it is updated from time to time. The next question is speech signal can be used in robotics as robot communication. Yes, indeed, speech is a natural way of communicating for a robot. There are examples of robots which can understand speech and take action as per the command. And it can also speak out. It can give information, and that information can come from the internet, for example, right? So home pods, for example, you can interact with them like Alexa and get information from the net. So they are also robots of some kind, right? So okay. What's next question? How speech, I think Uh, that question is not completely given. The next question is, can you please tell the difference between speech signal and environment sound? Like you have told about aircraft sound, gun sound, okay, and how we should deal with it. So environment sound, I mean, see, we talk of signals which are of message bearing signals, which could be speech signals, mostly speech signals, and then other sounds which we would call as noise, and which is something which has to be removed. Now, in a normal video conferencing scenario also, there would be noise coming from, let's say, an air conditioner or fan, or there could be people who are talking amongst themselves. So that is also some sort of an interfering signal which is coming from the environment. Now, all these have to be quietened or attenuated, and only the signal of importance should be transmitted to the far end. So that requires things like beamforming and localizing the source, some of which you will get to learn in the course of in the future lectures.
Sir, may I interrupt, sir?
Yes.
So my
Yes.
question was basically like speech. You have got that phonetics and different characteristics. But when we talk about environmental science, vehicle classification on the basis of sound signal, and gun classification.
Yes.
So in those cases, what things we should take care of, or how
Yeah.
is it different
So
from
that
the
is a
speech?
good question. Yeah, that's a good question. So, in fact, speech has this. So, you can do speech recognition, but then when it comes to, let's say, even music, there is, as we will see very soon, there is a speech signal production model. So, you can, from the signal, you can try to get back to the model and try to analyze and find out what was spoken. And that is not so easy for even for music, because music itself doesn't have a particular production model. You have different kinds of instruments with different models, and likewise other environmental sounds like guns and other machinery. So there is this preventive maintenance also that happens, and that is based on distinction of sounds in terms of any problems in gears, etc. So these kind of analysis are done typically in. Earlier it used to be done by people listening to it, and then one can automate it also to find out problems and for predictive maintenance purposes. So here the analysis tools are typically in the time domain. Some of those we will discuss today. In the frequency domain, the spectral related information, right, or time frequency. So these are signal processing tools to analyze sounds which are non-speech sounds for classification and other purposes.
Thank you, sir.
The next question is, does normalizing speech features like pitch, frequency aid in recognizing the speaker with higher? Yes, indeed, there is something called not pitch, but more so. The question is related to speaker in recognizing the speaker with a higher recognition. Yeah, so if you're talking of speech recognition, there is something called vocal tract length normalization, which is done in the classical approaches to speech recognition, which helps in improving the recognition accuracy. The speaker recognition, basically the distinguishing characteristic is the pitch frequency. One of the distinguishing characteristics is the nominal pitch frequency. So differences can be used as an aid to recognize speakers apart from other features. Any other questions? Okay. So shall we continue with the next session?
Yes, sir. We can continue.
Okay.
There are no more questions in the chat box,
Okay.
and
Right. So now let us have a brief understanding of the speech signal production model. So first we will look at the model for voice speech utterance. Now, as I discussed earlier, that air comes up from the lungs, it forces its way through the vocal cords and it pushes the vocal cords to open. And then when the vocal cords open, air rushes out through it, which causes the air pressure to fall. It follows Bernoulli's principle over here, that P1 V1 is equal to P2 V2, where P is the pressure and V is the velocity. And as the velocity of air increases, the pressure falls. And because of this drop in pressure, the vocal cords again close. Right? And when the vocal cords close, the pressure builds up behind the vocal cords and it again forces it to open. So this is the periodic opening and closing of the vocal cords, which is the cause of voiced sound or voice speech production. And the single cycle is typically of the order of 1/100th of a second, and this is called as the fundamental frequency. So the way this is modeled in the most basic form is that you have the pitch period as an input, or correspondingly the fundamental frequency as an input, and you have an impulse train generator, right, which generates a train of impulses, and you have a glottal pulse model, which is basically a model of the volume velocity of air that gets into the vocal tract. So its shape is something like this, as I have drawn. So this is the volume velocity of air. So the volume velocity, so basically its units would be something like centimeter cube per second. So it increases, and then suddenly, because of the drop in pressure, the vocal folds close. So there is a sharp closure, and then again after some time it opens and closes. So the impulses are input to this glottal pulse model, and then you can suitably scale by an amplitude gain factor AV, and the output of this is the glottal signal, that is UG of N. So this is part of the model. We will complete it as we go along. And in the frequency domain, we have the corresponding plots. So a train of impulses in the time domain would lead to a train of impulses in the frequency domain, which are separated by F0. The glottal pulse model has a roll-off of 12 dB per octave. So when the impulse train passes through this glottal model, the output has a shape as shown in the figure. So this is the glottal volume velocity signal that I drew in the previous slide. It is centimeter cube per second. And the shape is approximately shown over here. So the glottis or the vocal cords, they open and close periodically. Now the average, so the range of fundamental frequency for male voices, adult male, typically varies between 50 and 250 hertz. For females, between 120 and 500 hertz, and the average values are approximately 132 and 223 hertz. Now, this volume velocity of air enters into the vocal tract. Now, the vocal tract can be modeled as a resonance tube. So, and again, at the simplest level, we can consider it as a straight tube. And we have all studied in high school physics that the tubes can be excited but if you blow air into it, and they give rise to resonant sound. In this case, we can consider that the vocal tract is closed at the vocal cords end and it is open at the lips. Right? So this is here and this other end is the glottis end. We can consider it to be closed, and air is forced through this, which gives rise to resonance frequencies, and these are shown over here. So since it is closed at one end, right, so you have minimum disturbance, and it is open at the lips end, you have the maximum spread. So you have a quarter wavelength. So if this is the length of the vocal tract is L, then the first excitation F1, first resonance frequency excitation F1 corresponds to a quarter wavelength, and then you have odd multiples of the quarter wavelength for the higher frequencies which are excited. So the average length of the vocal tract for an adult male, let us take it to be 17.5 centimeter. And if we assume the speed of sound in air to be 350 meters per second, then you can work out from simple high school physics that the corresponding resonant frequencies F1 will be 500 hertz, F2 is 1500 hertz, F3 is 2500 hertz. So indeed, these are the resonance frequencies for the neutral vowel, the sound, neutral vowel, in which the tongue is in the central and mid position. It's also called as the schwa vowel. So for an adult male with average vocal tract length, this will be the frequencies, the formant frequencies for this neutral vowel. And for other vowel sounds, since the vocal tract shape changes, the combination of F1, F2, and F3 will accordingly change. So we now have this signal which gets into the vocal tract, that is UG of N from the earlier slide. Now we have to model the resonances of the vocal tract. Now the resonances of the vocal tract are the frequencies, the formant frequencies F1, F2, and F3. And these can be modeled, for those of you from electrical or electronics background, can be well modeled by an all-pole filter, where the zeros of the denominator polynomial or the roots of the denominator polynomial would correspond to the formant frequencies F1, F2, and F3, where you will have peaks. So, and now the output of the vocal tract model is then fed into what is called as the lip radiation model, which acts as a high-pass filter, because that is how the volume velocity signal is converted to a pressure signal, which then propagates in the air. So the lip radiation model converts the air volume velocity signal to a pressure waveform at the lips. So in a nutshell then, this is the overall model, which is called as the source filter model for voiced speech production. You have an impulse train generator. So the middle panel here shows time domain plots, and the lower panel shows the corresponding spectral plots. So the impulse train generator in time domain and in frequency domain. So the separation between successive impulses is the pitch period P, and in the frequency domain, the harmonics of the fundamental would be separated by 1 over P, which is F0. Then this is input to the glottal pulse model, which corresponds to the opening and closing of the vocal folds, which allows a certain shape of the volume velocity signal to pass through into the vocal tract. Then the vocal tract itself can be modeled as a linear time invariant filter for short durations, or it can be modeled as a block adaptive filter, where in each of the blocks corresponding to the stationary interval of the signal, which is about 20 to 30 milliseconds in duration, we can model it by an all-pole filter. So it will have a transfer function, and the frequency response would essentially give you peaks corresponding to the formant frequencies. Right? So in this case, F1, F2, F3 are the resonance frequencies which are excited in the vocal tract. The output of this signal is notionally gets into a lip radiation filter, which is a high-pass filter, and the output of this is the pressure signal, which is what propagates it, be heard by be recorded by a microphone. So this is the basic model of voice speech production, also known as the universal speech production model, when we include the model for the unvoiced part also. Now for the unvoiced part, the air comes up from the lungs, the vocal cords are open, air passes through unobstructed, and then if the air moves very quickly, a turbulence phenomena is created, and sometimes we create constrictions in somewhere in the vocal tract, as we have seen from the above examples of consonant utterances, and that causes random flow of air or turbulent airflow. So this is modeled usually by a random noise generator, and then you have an amplitude modification by AN, and the output of this is the volume velocity signal into the vocal tract for unvoiced sound generation. So for unvoiced sounds, then we have a white noise generator which goes into the vocal tract, which essentially introduces resonances, and then that is input to the lip radiation model, which converts the volume velocity signal into a pressure signal, and the output of this is the pressure signal in the air. And as you can see here, it is more random than a voiced speech signal. So these two, that is the models for unvoiced and voiced speech, can be combined into what is known as the universal speech production model, or the source filter model for speech generation, which comprises of an excitation signal, which is essentially the volume velocity signal into the vocal tract. And you have two paths. One is for voiced speech and the other is for unvoiced speech generation. The vocal tract creates resonances, F1, F2, F3, and then you have a high-pass filter, the output of which is the speech signal. Now, this is a very basic model. However, even the most sophisticated applications are essentially coming from this basic model. There are very few modifications, like the excitation signal, instead of being either something for voiced and something else for unvoiced, could be slightly more sophisticated. But then you have the vocal tract and the lip radiation filters, and this kind of models are the basis for most telephony applications. When, for example, you do communication on your mobile phones, then the speech signal is modeled in terms of a speech production model, which is very similar to this model with some modifications. and it is updated every 20 milliseconds or so, corresponding to the stationary interval of speech. So the parameters which are derived for speech signal are then used for transmission to the far end, which is then used for decoding the speech that you listen on your mobile phones. So what I'm trying to say here is that this is, although very simple, a very powerful model that is the basis for very many applications related to speech. With this brief background on the basic speech production model, now let us look at the different methods of processing speech signals. Any questions? Okay. So now let us first look at time domain processing of speech. So now we will look at some basic tools for analyzing speech signal, which will hold for the analysis of other kinds of audio signals also. And those analysis can then be used to make inferences or conclusions for those applications. So for example, one of them is the short time energy function. So we have the speech signal in the top panel, and the lower panel we can multiply it by a window function as shown over here, and then we take sum of squares, which will give us the energy of the signal in this window. And this window can then be slided, and you can then find the energy as a function of time n. Now this becomes relevant in the case of speech, because as we have seen, the energy changes depending on the kind of the utterance. So here we have the sentence, "what she said," and we compute the short time energy using a rectangular window as shown in the previous slide, but with varying length n equal to 51, 101, 201, and 401. And we see that in some portions the energy is high, and other portions the energy is relatively low. And as the window size increases, the plot becomes a bit smoother. Now we expect that the energy will be relatively high for voiced sounds, and in particularly for vowel sounds, and it will be low for unvoiced sounds like unvoiced fricatives, or in the case of stop consonants before the release of the air pressure. So short time energy function can be an indicator as to whether the speech is, firstly, whether speech is present or not, whether it is speech or silence, and secondly, if speech is present, then whether it is voiced or unvoiced. However, this by itself cannot unambiguously tell you whether it is silence or voiced speech or unvoiced speech, because these are overlapping segments. Sometimes if you have background noise, then the short time energy may not be very less, in which case one should not confuse unvoiced speech by silence. So these are some of the pitfalls of determining whether the segment is silence or unvoiced speech or voiced speech if you use only one function like the short time energy. But you can combine this with other measures which can help improve your inferencing. So another one is the zero crossing rate. So the average short time zero crossing rate, so as the name implies, it is the expression is given below. That is the sign change, how many times the sign of the signal is changing in a given window, right? And that is normalized by the window length n. So that is called as the zero crossing rate. Now, if you have a signal which is periodic, versus a signal which is random, right? So we expect that the random signal is going to have a much higher zero crossing rate compared to a periodic signal whose zero crossing rate would essentially be twice of f naught, or whatever is the frequency of the signal. Now, this then is again a very simple tool to analyze whether a given segment of speech is voiced or unvoiced, because unvoiced speech, as we know, is more random noise like, and therefore it is likely to have higher zero crossing rate compared to voiced speech. So here we have three panels corresponding to three different sentences. The top one is, "This is a story." So if we look at it, the "sir" part is strongly unvoiced, and this corresponds to this higher zero crossing rate. Then "is a story." Now, this "sir" of "is" and "story" are combined over here, this being a very short utterance. Right? So here again, because of the unvoiced segment, we have a higher zero crossing rate. And likewise, one can try to argue in the other figures regarding the unvoiced regions giving you higher zero crossing rate. For example, if we look at the third plot, "what she said." So "sh" and that is higher zero crossing rate, and then "she" E part is a vowel, so here you have lower zero crossing rate. And then again "said," the "s" part here has a higher zero crossing rate. So we see here that zero crossing rate gives you further information as to whether the signal in a given segment is voiced or unvoiced. So you can combine this information with the short time energy information to get a better estimate as to whether a given segment is voiced or unvoiced. Another such time domain measure is the short time autocorrelation function. So the autocorrelation function, as we would know, is given, the short time autocorrelation function is given by the expression over here. It is a function of the location of the window, that is n, and k here corresponds to the delay of the autocorrelation function. Now, if the signal is periodic, then we expect that the autocorrelation function is also periodic for an ideal periodic signal. Similarly, if the signal is approximately periodic, then we can expect to see peaks in the autocorrelation, the short time autocorrelation function, right, as we can see over here. On the other hand, if the signal is random noise like, then we do not see peaks in the autocorrelation function beyond the delay that is 0 or very close to 0. So one method to distinguish voiced speech from unvoiced speech is look for these periodicities in terms of peaks in the autocorrelation function. If such peaks are present, I am discounting the initial peaks over here. So in what is called as the pitch period range, because pitch periodicity is what contributes to the repeated nature of the waveform and the higher correlation. So if the signal is voiced, then we expect to see such peaks and that is enough correlation at longer delays corresponding to the pitch period. If the speech signal is unvoiced or random noise like, then the maxima will be very small compared to what we see in the autocorrelation function for voiced speech. So here again is another tool which can be used to distinguish voiced speech from unvoiced speech. So one can derive a cost function based on these kind of measures like the short time energy, the zero crossing rate and the autocorrelation maxima to infer as to whether a given segment of speech is voiced or unvoiced. And similarly, one can use these tools to determine whether the given region segment is silence or it is speech. Now, so just to add to this, now this period, the peak that you have in the autocorrelation function also can be used to find the pitch period. The pitch period peak, right? So this, if you have a periodic signal, then there will be peak at delay P, 2P, and so on, which can be used to determine the pitch period or the corresponding fundamental frequency F0. And now, a basic application of this method generally leads to errors because sometimes the peak at twice the pitch period, that is 2P, may be higher than the peak at the pitch period P. In which case you would wrongly estimate the pitch period to be double that of the true pitch period. So this is what we see in the top plot over here as a function of the window number or the frame number. So one has to apply what is called pitch period or pitch trajectory smoothing, which can use things like median filtering, etc., to find out the true pitch period and remove these errors that we see in the top plot. Now we can see here that the pitch period of a person doesn't change drastically from one frame of 20 milliseconds to the next frame. It changes smoothly. One can change one's pitch period or the fundamental frequency or the pitch frequency over time, but that cannot happen randomly or drastically. So this physical limitation is used as the basis for smoothing the pitch period or correcting the pitch period estimation, which otherwise can be erroneous. Okay, next, analysis of speech is very important, which is called linear prediction analysis or linear prediction coding, LPC. Linear prediction coding or LPC. And we will see why it is important. So we have looked at whether the speech signal is present or absent, or whether a segment is voiced or unvoiced. From the previous analysis, one can do it fairly accurately. Now let's concentrate on the vocal tract. The vocal tract, as we discussed, is responsible for the creation of resonances, and we can model these resonances as an all-pole filter. And since the resonances change over time, the all-pole filter has to be time varying. In fact, what is done is it is made block adaptive. That is, for a particular block or duration of time, which is typically 20 or maybe it is assumed to be fixed. So we estimate the transfer function for that duration of time. So Hz, which is equal to 1 upon Az, which is an all-pole filter, models the vocal tract system. So now we can estimate the vocal tract model from the recorded speech signal And the output of the inverse of the filter AZ is the residual signal, or vice versa. We can take the residual signal, which ideally is the input to the vocal tract, and the output of that is the speech signal. So 1 over AZ models the vocal tract resonances. So just one or two slides of mathematics to explain the problem. So the problem here is to find the coefficients of this all-pole filter, that is A1 to AP, to minimize the squared prediction error. So S of n here is the speech signal for a given duration, typically 10 to 30 milliseconds. S dash of n is an estimate or a prediction of the signal S of n, and that is obtained by a linear combination of the past samples. E of n is the prediction error, the error between S of n and the prediction S dash of n. And the way to find A1 to AP is to minimize the squared prediction error. So the squared prediction error EP is given by summation of E square of n. So which we substitute from the previous equation over here. Now we differentiate this EP with respect to the variables, that is the AKs, which leads us to these set of equations that is written in the last line. Or when we gather these on the left hand side and the right hand side, then this becomes the set of equations that we require to solve in order to get the AKs. Now, these are a set of linear equations that one requires to solve. Linear in the variables AKs. The term in the summation over here are essentially correlation terms which are found from the recorded speech signal. So there are two slightly different solutions which can be obtained to the above set of equations depending on the limits that we impose on n, on the summation n. And these are called the autocorrelation and the covariance method. So we will not go into the details over here, but just for your knowledge, and which you can look up later on if indeed you want to go deeper into this. Okay. So with this, then we can find the AKs, and therefore we can find the optimal all-pole filter, which in turn represents the vocal tract resonances which we use in the speech production model. So in a nutshell, this is how we can find the filter. Now let us briefly look as to what is an optimum value of P, that is the order of the filter. So here we see the speech signal and the 10th order LP residual. That is, if we take a 10th order filter, then E of n, which is the difference between the speech signal and its prediction using the optimal filter, is E of n. So we see that the error signal is relatively very low. It is random noise like when you compare it with the speech signal from which it has been derived. Okay. Now in this figure, we see the frequency response of the filter 1 over A1 e to the power j omega, magnitude of this, for unvoiced speech on the left hand side and for voiced speech on the right hand side. So the black line over here shows the magnitude Fourier transform of the signal from the noisy part, as you can see over here, P for the utterance S. And the blue line over here denotes the frequency response of the vocal tract filter, which has been modeled using the previous equations. So we see that this blue line essentially encompasses the Fourier transform. In fact, it is called as the spectral envelope. It determines the spectral envelope of the signal. Likewise, on the right hand side, we have taken a voiced speech signal, the vowel utterance E, for which the linear prediction analysis has been done, and we plot the Fourier transform of the signal, short duration signal of 20 milliseconds in black, and on it we have superimposed the frequency response of the vocal tract filter, which has been determined from linear prediction analysis. So again, we see that the blue line essentially forms the envelope of the signal spectrum. Now, what is an optimum order of the filter? So this we will see from succeeding slides here. So this is the spectrum of voice speech for a duration of about 20 milliseconds. And on this now, what we will do is to determine optimal filters of higher and higher order, and see how well it models the speech spectrum. So here we have superimposed a second order filter, which is to say 1/1 minus A1 Z inverse minus A2 Z to the power minus 2. Then we consider the sixth order. So we see that the sixth order filter, all-pole filter, models the envelope of the spectrum much better than the second order. Now, if we increase it further to a 10th order, we see that the 10th order models the envelope even better. For example, the peak over here in the spectrum, which was missed by the 6th order, is getting well modeled by the 10th order. And if we go further to the 16th order, then we see that there is not much difference in a 16th orders in the frequency response from a 16th order all-pole filter compared to the 10th order. So it may be doing a slightly better job, but then for practical reasons, we restrict to a lower order. So indeed, for telephony applications and many other applications, we consider a 10th order all-pole filter to model the resonances of the vocal tract. And these set of slides show why a 10th order all-pole filter is a reasonable choice. Okay. Now with this background, now let us spend a few minutes on the human hearing process. So auditory perception phenomena and conceptual domain analysis of speech. So the human auditory system is the other half of the whole process, and a good understanding of the hearing mechanism is also useful in developing applications. So briefly then, the human auditory system, which has been sketched over here, comprises of the outer ear, whose job is to provide protection to the overall ear. It collects sound waves preferentially coming from the front, and it does amplification and it funnels the sound wave into the ear towards the eardrum. The outer ear ends at the eardrum, which vibrates based on the sound that is funneled into it. Then we have the middle ear, which extends from the eardrum to the inner ear, which is shown over here as the region of the oval window. So the middle ear acts as an impedance match between the air-filled outer ear and the fluid-filled inner ear. It translates vibrations from the membrane to oscillations of fluid in the inner ear, and it also provides amplifications. There are other functions of the middle ear also, but we do not have the time to get into it right now. Then we have the inner ear, which basically is shown over here in terms of the cochlea. You see these rotating tube of unequal diameter or changing diameter. It becomes smaller and smaller as it goes inside, and different parts of this tube vibrate preferentially to different frequencies, and these vibrations are then transmitted through the auditory nerve over here to the brain for understanding. So basically here the mechanical vibrations get converted into electrical signals in the auditory nerve, which then goes to the brain for understanding. Now, in the subsequent few slides, I will explain some of the important auditory perception characteristics. One of them is called as the critical band phenomena. Now, according to this, the human ear, different portions of the inner ear are sensitive to different frequencies. So, if there are two frequencies in the neighborhood like this, then one of them may get masked because of the presence of the other tone. So this is in the frequency domain, F1, F2. And this happens if these frequencies are very close to each other. If they are outside a certain limit, then the presence of F2 hardly has any effect on F1 and vice versa. So this is known as the critical band phenomena. That is, the effect of frequencies extends to a certain band around it, which is called as the critical band. And the critical band width is as shown in the figure here, which is constant up to 1 or kilohertz or so, and thereafter it increases almost exponentially. So for example, then if let's say I have a center frequency of 500 hertz, right, and the bandwidth is 110 hertz. So if there is a dominant sound at 500 hertz, then another sound within plus minus 55 hertz of this will be masked by this sound. However, if the other tonal is outside this bandwidth, then it hardly matters. That is, the other sound would also be perceptible. So this is one phenomena which is exploited in the design, particularly of audio codecs like MP3 codecs are designed heavily based on this phenomena. It is used to reduce the bits for representing the threshold of audibility. So as a function of frequency, on the y-axis you have the sound pressure level, and you have this dashed line at the bottom. So any sound pressure level which is below this at a given frequency will be inaudible, and anything above this will be audible. So we see that at certain, so it is not that for all frequencies the sound pressure level is the same. lower frequencies require a higher sound pressure level in order for it to become audible. And associated with this is the notion of equal loudness. So these solid lines are lines of equal loudness, which means that a sound of a certain frequency on this line, that is for a given sound pressure level, will be equally loud as another frequency with a different sound pressure level on that line. So let us take one example. So if I take 200 hertz, then let's say we have a tonal sound which is 50 decibels, then that sound will be judged to be equally loud as a 4000 hertz tonal sound, which is about 42 decibels, that is 8 decibel lower, and vice versa. So this is the notion of equal loudness. That is, different tonal frequencies have to have different sound pressure levels in order to be judged as equally loud. So this is another auditory perception phenomena. The third characteristic is that of frequency domain masking. Now, if I have a tonal sound, let's say at 1 kilohertz as shown in this figure, then the dashed line here shows the threshold of audibility. The threshold of audibility gets modified due to the presence of this tonal sound at 1 kilohertz, so that the new threshold of audibility is as shown by the solid lines depending on the loudness of this tonal sound. What it means is that, let's say there is another tonal sound which is of a certain level, let's say a 2 kilohertz tonal sound which is of 20 decibel. Now, if we did not have the tonal sound at 1 kilohertz, then this would have been audible because it lies above the dashed line. The 2 kilohertz sound would have been audible. However, now we have this 1 kilohertz tonal sound, let's say of the 60 dB level. Then the threshold of audibility gets modified and the 2 kilohertz tonal sound would be barely audible. Or if, for example, the 1 kilohertz tonal sound was of 80 dB level, then the 2 kilohertz tonal sound would become inaudible. So this is the phenomena of frequency domain masking, that is, one sound getting masked by another sound. And this phenomena is not limited to only tonal sounds, it also extends to broadband noise. Okay. This I'm just repeating, this has been discussed. And the last important characteristic that I want to mention about is that masking is not only a frequency domain phenomena, but it is also a time domain phenomena. So here I give examples of forward masking and backward masking. So what is forward masking? So if there is a noise which extends up to a certain time, as shown over here, and there is a signal which comes a short time after that, then because of the intensity level of this noise sound, which may be of certain duration, the signal which comes later on may get masked. And that depends on the duration of time after which the signal arrives. So this is called the phenomena of forward masking. Similarly, we have the phenomena of backward masking, which is that if I have noise and then the signal has arrived just before the noise begins, which is a few milliseconds before that, then this signal may also get masked. That is, you may not be able to hear this sound. Now, on the face of it, this appears to be a non-causal phenomena because the noise sound which is masking the signal of interest comes later on, But then there are explanations, very valid explanations. Again, we do not have the time to get into those explanations. But these are phenomena of the human ear, that is time domain masking in the form of forward masking and backward masking. And the degree of masking, that is this time t that is indicated for forward and backward masking, to which this is effective, the masking is effective, depends on the level of the signal or level of the noise that is masking it. So that is explained in the figure over here. Okay. Then auditory perception characteristics. So binaural hearing. So 2 ears help localize the source of sound in the horizontal plane. The sound source localization accuracy, this depends on either the time difference of arrival of the signal in the 2 ears, which is effective at low frequencies, or the level or amplitude difference of the signal in the 2 ears, which is effective at high frequencies. Then we also have the phenomena of front-back ambiguity, and also the ear is able to have some resolution in terms of the height of the sound source, which is facilitated by the shape of the pinna or the external part of the ear. So this brief exposure or expose essentially gives you a feel of the various phenomena in the human ear which are relevant in order to develop applications. And I'll briefly mention one of these, which is the cepstrum, which is used or which is derived from the human ear phenomena and is used heavily for speech recognition applications. So what is cepstrum? So the speech signal may be considered as a result of convolving excitation signal with the vocal tract. Right? So cepstrum can be used to deconvolve the two components, that is the excitation signal, which is input to the vocal tract, and the vocal tract impulse response. So the definition of the cepstrum is basically the inverse Fourier transform of the log of the Fourier transform of the signal. So you take the Fourier transform of the signal, take the logarithm, and then you take the inverse Fourier transform of, and of course in between you have the magnitude also. Otherwise it will be a complex number in general. So here are examples of the cepstrum computation for vowel sounds like E. So this is an almost periodic sound. We take the Fourier transform using the DFT and take the log magnitude. So this is the log magnitude plot. And then we take the inverse Fourier transform, which gives us the cepstrum. And in the cepstrum, the point to note here is that there would be peaks if it is voiced speech. Then there would be peak corresponding to the pitch period delay, which is also referred to in the cepstrum literature as Q-frenzy or a jumbling of the word frequency. So the presence of these peaks over here are indicative again that the speech signal is voiced, and what is the pitch period corresponding to the voice signal can be found from the cepstral analysis. Fine. Likewise, we plot the cepstrum for unvoiced speech, in which you will not have such a peak. It is fairly flat throughout as a function of the time. Now, we have a scale in the frequency domain, which is called the Mel scale, which is understood as follows. The human ear has a better frequency resolution at low frequencies. So we need to discriminate between speech sounds using as few parameters as possible. Remember that when we say discriminate speech sounds, we are pointing towards the application of recognition. We want to discriminate and recognize speech sounds. And this we want to do with as few parameters as possible, which will then constitute the feature vector. So as we know that when we want to classify, then we construct feature vectors. And feature vectors should basically have as few parameters as are necessary to do this discrimination. So the MEL scale, the word MEL comes from, the term MEL comes from the word melody. It relates the perceived pitch to the frequency. So this is a MEL scale, which is again, derived from the human auditory perception, and it is similar to the critical band relation. So what is used in speech recognition almost universally are MEL frequency Kepstrom coefficients, MFCCs. So basically how is MFCC derived? We have MEL spaced filter bank. So you have this bank of filters over here. You have the speech signal, take the magnitude Fourier transform and its square, pass the signal through this bank of filters, take the energy at the output of each filter, take the logarithm and the inverse DFT. The point to note here is that the bandwidth of these bank of filters changes. In fact, it increases as you go to higher and higher frequencies. And this is based on the human auditory property that we discriminate sounds at lower frequencies much better than at the higher frequencies. So therefore, the features are constructed at the output of this inverse DFT filter, which is inverse DFT, which are called as the MEL frequency Kepstrom coefficients, which form the basis of speech recognition. So acoustic features used in speech applications are MEL frequency Kepstrom coefficients. The MEL scale approximates the response of the human ear. Something similar to MFCCs are also perceptual linear prediction coefficients, which are derived from linear prediction coefficients. And in addition, what we use are what are called the difference or the double difference or delta and delta coefficients, which are derived from the MFCC coefficients, which incorporate the temporal dynamics. That is, delta coefficient, delta MFCC corresponds to the difference of the MFCC in succeeding frames. And so this part I just mentioned to complete the discussion, that is the Kepstrom analysis, which is used again for pitch determination and voicing determination, and also its relation, its use in speech recognition through the MEL frequency Kepstrom coefficients. So with this, then we come to the conclusion of this lecture. Of course, there was a lot of material, some of which I had to rush through, but it gives you an idea, especially for those who want to get deeper into speech or more generally into acoustics or audio signal processing, as to the various kinds of tools in the time domain, the frequency domain, the time frequency domain, and the cepstral domain, which are useful. These are simple tools, but they are very useful in the analysis of speech for various applications. So to conclude then, decades of focused research by key research labs and universities has paved the foundation for deploying speech applications on a large scale at affordable costs. We are all aware and have used speech applications at some point or another, whether dictating what you want to type on your phone, or listening to the computer speak out. And these have improved drastically in the last decade, which is why it is being now used on a wide scale by the general public. Significant domain knowledge, that is the characteristics of the speech signal and the human hearing process, is necessary in developing efficient applications. Uh, so that's why we went through this lecture. That understanding of the different characteristics of various speech sounds is important if you really want to develop efficient applications. Simply applying, like nowadays you have learning, deep learning techniques, etc. But one can do apply deep learning techniques blindly, but a knowledge of the speech production or the signal of interest, that is the domain knowledge, becomes important ultimately in developing efficient applications. A lot of the work in speech processing is language specific, and there exists large scope of R&D activities in speech processing in the context of Indian languages, particularly in the context of what I mentioned at the beginning of this lecture. That is, a lot of thrust is being put in the development of tools for so there are various groups of researchers as well as startup companies which have been involved in the development of tools which ultimately would be freely available, and anyone can use it to develop applications, whether it's related to speech recognition or machine translation or text to speech synthesis, or combining all of them to develop speech to speech translation engines. So with this, I come to the end of the lecture. So here are some important classic references which those of you who are interested can go through, and then I can take up some more questions.
Thank you, sir. Thank you very much. Uh, there are a few questions in the chat box that I can see.
Yes.
Uh, First, Muhammad Ashraful Khan, he is asking, why is human auditory system more sensitive in between 2 to 5 kilohertz?
Okay. It's there is a physical reason, which is that the outer ear can again be modeled as a resonance tube, just like we saw that the vocal tract can be modeled as a resonance tube. So the human ear, which is can be considered to be closed at the eardrum end, and then taking the length of the outer ear, you have the first resonance and the second resonance, and those fall at the certain frequencies. So if you look at the plot of the threshold of audibility, then you have these dips. This is one dip and this is another dip. This corresponds to the first and the second resonance of the outer ear canal. Now, there is also another explanation as to the evolution process, wherein it is said that most of the sounds that are important from the perspective of threat to human beings, I mean, it is most of the evolution process, human beings have been staying out in the open, and the sounds which cause threat to the human being lie in this band extending from 1 kilohertz and above. I mean, and therefore the evolution of the human ear has happened in a manner that it is more sensitive at these frequencies. So there is a whole lot of literature which discusses on the evolution of the human vocal tract system, the speech production system, and the human ear simultaneously, how it has happened over hundreds of thousands of years. So if you are interested, you can look into that literature also.
Okay.
The next question.
Yes,
Sorry.
thank you, sir. The next question is by Dr. Prashant Upadhyay. The first part is, what is the basic difference we observe with Mel scale and Bark scale? Does it also depend on the application for which we are using?
No, so the Mel scale and the Bark scale are approximately the same. So one can use one or the other. It is just that the Mel scale has evolved for MFCCs, but they are approximately the same. There is no difference. Practically, there is no difference.
Thank you, sir. And another question by Mr. Yash Pratap Singh. Sir, can we use match filter to reduce mean square error?
See, the matched filter means it is matched to something. So that something, that some signal has to be known. So now when we are speaking, essentially, we do not know what we have to match to because the signal varies. In fact, what we talk, the same sound next time we speak will be different. So unlike in communication, where we know what we are transmitting, and therefore matched filter is very useful in communication applications, in speech processing, I do not see its use.
Okay, sir. And then the last question again from Dr. Prashant Upadhyay. Okay, I've got more questions. Sir, can you tell us more about the project which you talk about in starting?
Yes, so that is the government of India's. Let me see if I have it here. Not here. Somewhere it should be. Maybe I can. Bhashini. So if you go to the portal bhashini.gov.in, then you can read about it. It says Bhashini aims to enable all Indians easy access to the internet and digital services in their own language and increase the content in Indian languages. You can also contribute to Bhashini in terms of giving some voice in your own voice, and that becomes part of a database which is then used to develop products. So you can read about it. Now, this has basically academic institutions who are building speech recognition tools, text-to-speech synthesis, and machine translation between all the scheduled languages of our country, and also some of the rare languages, Northeast languages, etc. Right? So Bhasha Dan, you can contribute to this. So there's a whole website, you can read about it. This is very ambitious. It was announced by the Prime Minister in the Independence Day speech in 2017, if I'm not wrong. And then after a few years, everything was conceptualized. And then from last year, the mission has started, and it is for a duration of 3 years. So not only academic institutes, so researchers from, at least 50 or 60 different universities and startups, etc., who have been asked. Projects have been invited from them. So all they are part of this mammoth exercise.
Okay, thank you, sir. Couple of questions from Lieutenant Agrahari. First question is there any model for sound localization which can resemble ear? And the second is there better method than MFCC for feature extraction in sound classification?
So regarding sound localization, if you want to do it by automatic means, then you need to form an array of microphones. And there are different architectures. Then why be limited by the human ear, which essentially has 2 sensors? You can do better than what the ear can do. And indeed, you can build sensor arrays of different architectures which can localize multiple sources of sound which are better than what the human ear can do. Coming to the second question, Is there a better method than MFCC for feature extraction in sound classification? People have worked on various kind of feature sets which are derived from speech production, from the human auditory system, but people repeatedly come back to MFCC because they seem to perform almost optimally compared to many other features. But having said that, there is a lot of literature available on other sets of features, and sometimes they combine it with MFCCs to improve the performance slightly. So all that is available. But if you want to do the maximum in a limited period of time, that is, let's say 80% of the accuracy in 20% of the time, then the first choice will be MFCCs.
Sir, sorry for interruption. One more point from the first question, sir. How much work have you done in AI part, sir, for localization? Is it like it is all signal processing, or AI can be built upon signal processing for localization?
AI can be built upon signal processing for localization. Our own study shows that it can give better results, and maybe some of the speakers will talk about it in subsequent lectures, that AI can augment classical signal processing techniques to give you better localization.
Okay, sir. Thank you, sir. I'll wait for that. Yes.
Thank you. The next question is by Ms. Rohan Nessa. The question is there any optimum choice for window duration to be employed for speech processing applications?
So we have two parts. One is the excitation part, which is basically creating the source signal, which is input to the vocal tract. Now, the excitation signal varies at a faster rate than the vocal tract resonances. So for the vocal tract, typically we have a duration varying between 10 to 30 milliseconds, which is assumed to be the quasi-stationary interval. But for the excitation part, that is, for example, the pitch period evolves at a faster rate, and therefore the analysis for pitch period or the excitation signal analysis is done at a higher rate, typically 2 to 5 milliseconds update. Otherwise, the choice of the window duration for applications such as coding comes from the bit rate that you want to work on. If the bit rate is low, then you would go for a higher duration of the window, so that your update rate becomes lower and thereby you achieve lower bit rate. So it may come from the application also, but typically 10 to 30 milliseconds for the vocal tract resonances or vocal tract parameters, and between 2 to 5 milliseconds for the excitation part.
Okay, sir. Thank you, sir. Last question again from Dr. Prashant Upadhyay. How voice signal are used to detect the human disease?
Okay. So human diseases can be of various kinds. Firstly, let us talk of, let's say, a tumor or a nodule in the vocal tract system, or paralysis of some part of the vocal tract. So from the speech signal, one can construct a movie of the vocal tract, how it is varying, right? So you have softwares which from the recorded speech signal can create a movie of how the vocal tract shape is changing over time. And this is used for non-invasive early warning systems regarding any paralysis in the vocal tract, or if there are lumps in the vocal tract. So that's one kind of disease analysis which has been around for quite some time. The other is uh, basically emotions. So the emotion of a person can be detected from the glottal volume velocity signal, and primarily, in fact, the ratio of the close to the open phase of the glottal volume velocity signal has been used to indicate the kind of emotion a person is experiencing. For example, a person is sad, or it's neutral emotion, or angry, or happy, or whatever. So typically 7 to 8 different kinds of emotions have been worked upon. And primarily the glottal volume velocity signal contains information about the emotion of a person. Then there is also for infants, infant cries are used to analyze the state of mind or what the child is trying to convey. So there are infant cry analysis. In fact, we collaborated with the All India Institute of Medical Sciences to make some softwares where professionals, doctors, and mothers were involved to annotate what kind of expression a child is giving. And we created a tool for understanding human cries, because that's the only way they express it, right? Not only way, but one of the important ways of expressing any difficulties. Now, so these are the different things that come to mind. If you have any particular disease, then you can ask about it.
Okay. Thank you, sir, very much. This is actually going late, and we started in from 7 and reaching 9:30. So this session, which is actually given as a mandate from the Atal, that we have to have this session in the evening from 7 to about 9:30. So it is between the dinner time and after the entire day's hectic work. You have given such a nice piece of information and probably motivated many of us to work in this important area, and given the basics uh, of what is to be covered in the future lectures that are there. So thank you very much, sir, for a nice presentation. And we are sorry that we are meeting online. Uh, if it was offline, then of course we would like to give you some sort of appreciation. As a token of appreciation, we could like to have some memento or something like that. But
Yeah.
what is possible is that we can have a virtual memento. And with this, I would like to thank you, Professor Arun Kumar Sahab, for giving your time and useful information to all of us. Uh, it has motivated a lot of young minds. And in the question or answer session, we have seen that there were many queries raised by the participants. And of course, I can see that many comments came that the session was very good. A lot of interaction was there. So, with this word, I would like to thank you very much, and I would like to uh, emphasize that the participants who have gone through this, please go through the slides also and the references that sir has given. They are very useful references. And uh, as you are aware that we will have MCQs also based on the presentation that has been carried out. So kindly go through that. And with this, I would like to stop over here. And may I request Dr. Wajid if he wants to add something?
No, thank you, sir. So actually, I requested Professor Arun Kumar for this lecture, and he, on the very first call, he agreed for this. And although this is very late evening, and I'm really thank you to sir for accepting the invitation and just delivering this talk. Thanking you very much, sir.
Yeah. Thank you. It was a pleasure to deliver the lecture and interact with all the participants. I could sense enthusiasm, and I'm sure that this will carry on in the subsequent lectures, and there'll be a lot of learning. And learning will only be useful when it is applied and some applications come out. So that should be the focus of basis for the learning. Thank you.
Thank you, sir. Thank you, sir.